Okay, so now I'll be covering the Kimberlites. So, Kimberlites are fascinating for a number of reasons because they are, potassic rich and they have typically ultra mafic hybrid rock that occurs in ancient cratons and they're volatile rich. They tend to rise from mantle depths so rapidly and violently. So, they contain diamonds and coesite. That is a high grade quartz, which indicate a fairly deep mantle origin. They also contain xenolith from deep mantle as well. The term kimberlite it was introduced by Lewis because there's this diamond-bearing porphyritic mica peridotite of Kimberley area of South Africa. And the petrography of kimberlite is both unusual and complex because they are the hybrid rocks that contain minerals, rock fragments, and they formed in diverse physical and chemical environments. So they vary greatly in model composition, olivine, serpentine groups of minerals, phlogopite, etc., etc. So if I say that it contains olivine is the most abundant mineral in it, but it may be partly, completely replaced by the secondary mineral that is serpentine. And there's abundance of phlogopite. Carbonate mineral is so highly variable. Kimberlite is divided into further groups. That is kimberlite, sensu stricto, micaceous kimberlite, and that I'll cover later. So Michel defined kimberlite as a porphyritic alkali peridotite containing rounded or corroded phenocryst of olivine, serpentinized, carbonatized, or fresh. Phlogopite is fresh or chloritized. So it contains this variety of minerals and a volatile rich potassic ultrabasic igneous rock that occur as small volcanic pipes, dikes, and cells, and it has distinctively inequigranular texture resulting from the presence of macrocrystal set in finer grain matrix. This matrix contains as prominent primary phenocrystal or groundmass constituents olivine and several of the following minerals, that is phlogopite, carbonate, and monticelite, apatite, minerals, perovskite, and ilmenite. Kimberlite olivine is the usually most abundant mineral, but it may be partly or completely replaced by the secondary mineral, that is serpentine. I've already told you. And some have the three generations of the olivine. The abundance of phlogopite and carbonate is so highly variable. Kimberlites can be divided into three groups, that is kimberlite, Stenostricto, micaceous kimberlites, and calcareous kimberlites, depending on the proportion of olivine, phlogopite, and carbonate. Kimberlites are currently divided into two groups. So the first one is group 1 kimberlites. So they are the archetypal ultramafic kimberlites. So they are first described from the Kimberley, South Africa, and it's known to occur on all continents. And the type 2, group 2 kimberlites are micaceous kimberlites, that is orangites, the occurrence of which presently limited to South Africa, and they are older, 100 to 200 million years than the group 1 kimberlites in same area. Okay, now we have the group 1. So they are volatile rich CO2 potassic ultramafic rock. In addition to their xenolith content, they commonly exhibit a distinctively inequigranular texture caused by the presence of rounded and annular fragmented macrocrust and in some cases megacrust set in fine-grained matrix. Some of these are xenocrust. Olivine is generally predominant but may be accompanied by ilmenite, pyrope, diopside, phlogopite, enstatite, and chromite. The matrix typically contains a second generation of fine-grained euhedral to subhedral olivine plus monticelite, phlogopite, perovskite, spinel, and apatite. They may contain a late polyclitic PA-rich phlogopite, and many kimberlites exhibit 10 sized round globular to amboid shape segregation masses of calcite plus serpentine. Group 2 kimberlites and orangites. So it has an texturally similar group to group 1 but are ultrapotassic peralkaline, and has dominant macrocrystalline groundmass phase, and the olivine is common although essentially as anarchist. Other characteristic primary phase include diopside, spinel, and perovskite. So mineralogically, they are similar to lamproids. Okay, and they are characteristically have high K2O, TiO2 than the one group kimberlite. Intergranular texture is also important, and yeah. So kimberlite का पूरा टेबल आपको दिया हुआ है. Emplacement बताई जाएगी यहाँ पे. Field relation and all. So diamonds basically occur in lamproids, kimberlites, and orangites. Emplacement. Kimberlite magma. They have to move rapidly through the lithosphere in order to transport relatively high densities analysis of mantle origin that they usually contain to prevent the resorption inversion of the diamonds they contain. Experimental studies of the primary phases that they contain and also generally demonstrate that kimberlitic magmas have equilibrated at mantle material at the depth of 200 km. So it is postulated that the magma has to travel rapidly through the lithosphere with the speed of 20 to 70 km per hour through a deep-seated fracture. If this occurs, a low viscosity fluid phase may separate from the magma wedge, open the fracture, first batch of melt, moving at speeds in excess of 25 km per hour. Later, a vent system develops and the later batches move at 70 km per hour. Kimberlite field relations and placement is given how at what speed it goes and all. So kimberlites and orangites, they occur as a hyperbasal dikes and sills, diatreme, crater fills, pyroclastic, depending largely to the depth of exposure and erosion. So dikes are generally 1 to 3 meter thick and commonly occur in swamps where they tend to bifurcate into anastomizing stringers. Most dikes tend to pinch out towards the surface and thicken with depth. Sills are less common and may be up to several hundred meters thick. Some dikes expand locally near the top into lenticular enlargements called blows, and which may be up to 10 to 20 times the dike's width, and 100-meter long blows may feed into the root zone of the diatrams. So diatrams is 1 to 2 kilometer deep carrot-shaped bodies with circular to elliptical cross-section, and they have steeply dipping sides that is up to 80 to 85 degree. They taper downward and terminate into root zone. So irregularly shaped multiphase intrusion transitional into the hyperbasal kimberlite orangites. Nature of the volcanic processes that produce diatrams is still in the subject of much debate. Diatrams represents the expansion of volatiles in the magma. It approaches to the surface and the confining pressure is lowered. Okay. That is not required. So diatreme facies, kimberlite orangites at least near the surface are more fragmented than their hyperbasal equivalents that take on the volcanic appearance. Breccias containing abundant country rock inclusion and subordinate earlier hyperbasal kimberlite orangite solid fragments from a few centimeter to microscopic size are most common rock type. Okay. Now megacrystal and microcrystal are also common, and the fragmental nature grades downward into non-brecciated kimberlites. Petrogenesis. So they have what? So kimberlite. Okay, the rock of kimberlite kindred are a paradox, as they generally have major element composition similar to picrites, that they are also rich in incompatible elements. Wegener and others have proposed that the kimberlite magmas are generated into a source region that is relatively deep within the mantle, and the magmas are the products of low degree of partial melting. This is known as incipient melting hypothesis. This hypothesis would only work if the source material had a special composition. They were phlogitic bearing lateralites, but one cannot explain the incompatible elements were highly concentrated in the source rock. Okay. After that, another hypothesis is residual liquid hypothesis. So it is based on the concept that possibly a genetic connection between the exclusion of flood of tholeiitic basalts and later emplacement of the kimberlites. So, as the termination of the period of active mantle convection and the exclusion of flood basalts, pocket of tholeiitic basalt magma remained in upper mantle. This magma cools under high pressure condition and pyromorphosite precipitate. Fractional crystallization results in settling of carnates, and this yields the residual liquids enriched in alkalis. There is a huge theory in that. So, what I want to tell is I have. Okay, just a minute. There's a huge debate on that. So I would suggest you to read. I would suggest you to pause it out and then read about it, because it is kind of typical. Okay, so from here. So we have this diagram. It's a hypothetical cross section of an Archean craton with an extinct ancient mobile bills, once associated with subduction, and a young rift is there. So low cratonal geotherm causes graphite diamond transition to rise in central portion. Lithospheric diamonds therefore occurs only in peridrites, eclogites of the deep cratonal root, where they are then incorporated into rising magma, mostly kimberlitic K. Lithospheric orangite so and some lamproid cell may also scavenge diamonds. Melitites M are generated more extensive partial melting of asthenosphere. Depending on the depth of the segregation, they may contain diamond. That may contain diamond. Nephlenites are and associated carbonatites develop from the extensive partial melting at shallow depth in rift areas. Kimberlites, orange and silicate rocks are there. So we have this garnet, hasbergite, eclogite, melts, diamonds. All are shown where they can be present and what will be the place. So it's a schematic cross section of Archean craton with Proterozoic mobile belt and a modern rift. Due to lower geothermal gradient in the poorly radioactive cratonal area, the diamond graphite transition is elevated into deep cratonal lithospheric mantle root. Okay. Diamonds occur in only in hazellite and depleted hasbergite donites of this rock and not beneath the rift or mobile belts. There are only melts regenerated in the beneath of this root can entrain and disaggregate diamond bearing. This word is not there. So kimberlite K, it may pass through various rock types, picking up hasbergite, eclogite, and hazellite xenolith. Lithospheric orangites may also travel diamond bearing levels. Lamproids may occur commonly in old mobile belts, and some may be generated in diamond bearing materials. And diamond occlusion are commonly eclogitic in diamondiferous lamproids, and the source may be remnant subducted slab within the oceanic crust. Now, they have basically told us about this all. N, M, M, K, K, O, L, K, etc. So this figure suggests that any melt that traverses the deep diamond-bearing horizon of cratonal roots may incorporate diamonds. Most melts rise sufficiently slowly and are oxidized enough to destroy any diamonds that may encounter. Kimberlite's Indian occurrences. So we have Vajrakur, Anandapur district, Andhra Pradesh. They have a cluster of pipes and they are considered to be intermediate between the type of kimberlite and olivine lamproids. Majvagan pipe of Andhra Pradesh is a typical example of micaceous kimberlite, and Chalema dike of Kurnool district, Andhra Pradesh, are considered to be kimberlite. Carbonatite complex has subsequently been described as olivine lamproid. Notes. All the exhaustive thing is done, but I would like to give you some short and crisp notes that would help you. So kimberlite मैंने बताया कि एक अल्ट्रामैफिक इग्नियस रॉक है, प्राइमरी होस्ट है डायमंड डिपॉजिट्स का, एंड दे आर मेंटली डिराइव्ड मैग्मास. ठीक है. सो डेफिनेशन, कोर्स ग्रेन्ड है, अल्ट्रामैफिक इग्नियस रॉक है, मैग्नीशियम मिनरल है, एंड डायमंड बीइंग नेचर आई ऑलरेडी टोल्ड यू. सिलिका कंटेंट वेरी लो, 35 to 50%. प्राइमरी मिनरल्स है ओलिविन, पायरोक्सिन एंड kimberlite mica. Accessory minerals are diamond, garnet, ilmenite, chromite, phlogopite, mica, calcite, etc. And petagenesis of kimberlite. Formation of kimberlite involves the complex interaction of mental processes and significant mental melting. So mantle source. Kimberlites are thought to originate from deep mantle. Within the depth of 150 to 450 km, they are associated with mantle plumes and hotspot. The source composition. The source of kimberlite is often carbonate, peridotite, eclogite enrichment, volatile components like CO2 and H2O. So kimberlite magmas may form through low degree partial melting, that is up to 1 to 5% of the mantle. And the melting process is driven by high volatile content, particularly CO2. So these magmas are typically rich in magnesium and rich in volatiles, the CO2 being a key component that promotes the formation of CO2 rich metals. Magma ascent and crystallization. So once formed, kimberlite magma ascends rapidly towards the surface, often with significant volcanic explosivity. So rapid ascent and pressure change can result into mantle xenoliths, that is garnet, diamond being entered in magma, giving kimberlites their unique characteristics. And as the magma cools, it crystallizes olivine, pyroxene, mica, and characteristic of porphyritic texture. So kimberlites are often typically volcanic in nature, form pipe-like structures, and tectonic settings of kimberlite formation. Kimberlite are found in tectonically stable region. They are most commonly associated with mantle plumes and hotspot. So kimberlites are, I've already told you, and where upwelling mantle material results in decompression melting from the south of the carbonated mantle. Kimberlites are often found in cratonic regions and a stable part of the Earth continental lithosphere, ancient mantle roots that allows the preservation of the diamonds and other mantle-derived minerals. Geochemical characteristics. Major elements are Mg and Fo, and low SiO2 and high CO2. Trace elements, they are enriched in LiLe and they are depleted in HFSe. Isotopic signature SR-ND isotopes generally have the mantle-derived isotopic signatures, and CO isotopes. So involvement of mantle-derived carbon, delta C values are shown. So the unique features are diamond-bearing nature, ultramafic composition, volcanic explosivity, mantle xenoliths, economic significance, contains gem quality diamonds. Okay, and classification is there is so many classification. Phosphoritic, tuffistic, mica, hyperbasal, etc. TiZr and NAB. So kimberlites have low TiZr, NAB, NBTA ratio, so low concentration of high field strength elements. Kimberlites are found in South Africa, Canada, Russia, Australia. So kimberlites are ultramafic, volatile, rich igneous rock that hosts diamonds. They are formed by low degree of partial melting, associated with metal plumes, diamond bearing, low SiO2, high CO2, mantles, analyth, and explosivity, and the primary source for diamond.